Hi, I'm Abhishek Kona. I'm a software engineer at Parse and Facebook. I hope you're having a good GopherCon so far. My talk is titled Rewriting the Parse API in Go. So let me, oops. So we at Parse rewrote our API stack in Go from Ruby over the last 2 years. I'll explain why we did it, how we did it, and I'll go through a few libraries and tools we built along the way. So what is Parse? Parse is a mobile platform to allow you to build an app without having any servers. It is what I call a backend as a service. You as an app developer just use the client SDK and build your app only in one language, kinda. Parse tries to take care of as much server complexity as possible. We have 3 main products: Parse Core, which is used to manage your data; Parse Push to send notifications; and Parse Analytics to track metrics. Parse was acquired by Facebook in 2013. That's how I ended up working at Parse. So how did the Parse stack look in 2013? It was primarily a Ruby on Rails app, 10 engineers working on it. We had around 60,000 apps using us, but we were starting to have problems. Our biggest problem was a single popular app could take us down. This happened once, actually. I think a Japanese app got really popular on some TV show, and they were like voting on it, and Parse was starting to page. And that's because we use Unicorn, our HTTP server. Unicorn has a fixed Unicorn worker pool per machine. So that means that when we have a traffic spike, we can quickly run out of Unicorn pools. This happened so quickly that our auto-scaling groups could not respond to it. So yeah, Unicorn is not very well suited for bursty traffic. Ruby also has pretty big deploy times. Our deploy model is we have to run bundle deploy on every node, which takes time. So our deploy times are pretty high. We could not get out changes quickly. The Ruby codebase was pretty hard to understand. We used a lot of gems, and these gems would at times monkey patch core Rails functionality. So while we were debugging a function, we could not know which line of code was actually being executed. So against popular wisdom, we decided to rewrite. Our reason for the rewrite was, when we rewrite, the new system would be much more stable. It would be more performant. Our deploy times would be lesser than what it is right now. Our tests would be quicker. Our Ruby tests took around 25 minutes. We claimed that if we rewrote the software, we could do a better job at tests. We wanted a code base in which new members could quickly join and start working on it. And they did not have a high cost to understand. To start working on a Rails stack, one had to understand how Rails worked, how to write a new controller, things like that. We wanted something which was much simpler. So we decided to rewrite in Go. Why did we pick Go? Go is a statically typed programming language. It has good concurrency support. We felt we could do things in background. The HTTP server in Go is made up of a dynamic number of Go routines. It does not have a fixed number of workers. So we felt that we could trade off latency for throughput under load. Go is very shiny. It is easy to attract engineers to work on. We actually found a lot of programmers wanted to write Go over C++. We tried to move our stack to the JVM via JRuby, but most of our gems were not thread safe. So we saw some crashes, and that was not really a solution for us. We actually liked .NET or C#, but it was not really open source at that point of time. So we went with Go. Parse being a developer platform, backward compatibility is important for us. We have some SDKs which are 3 years old. out in the wild. They still send us requests. Breaking our API would break those apps. At any given point, on any day, we have around 600 OS SDK pairs sending requests to parse. So there was no real easy way for us to break our existing APIs. So our rewrite had to be fully backward compatible. We did not want to have any downtime while we were doing this. This was kind of hard because as we were rewriting our software, we kept growing our stack. Our traffic kept growing. We started to add more and more backends and databases. We were also doing product development. So it was a little bit of chasing a moving target. And we did not want to have any downtime during this rewrite. It was kind of like changing the engine of a moving car. We did not just start rewriting our entire stack in Go. We actually started with a few experiments. We first built a completely new product in Go. It's called parse hosting. Parse hosting is a service which allows you to host dynamic or static websites on parse. So we built this product entirely in Go. Ruby was not very well suited for it because it needed to do quick restarts and SSL reloads, and we felt Go was better suited for it. So we built the service very quickly. It was very easy to deploy and maintain. We were very impressed with the standard library. So we felt that Go is a good language to move forward with. Next up, we went for our most problematic service at that point of time. It was called parse push notification service. It is a service which opens long-lived push sockets or long-lived socket connections to Android clients. This was before GCM. Parse push notification service was written event machine and Ruby. It was breaking down. We were having memory issues, connection issues. So we rewrote this in Go, and we were very happy with, again, the performance numbers. We went up to 1.5 million connections per node from around 250,000 in Ruby. So yeah, at this point, we were very impressed with Go. And we started rewriting our API server in Go. But during this time, we had another issue. Our primary database, Mongo, had a hard connection limit of around 20,000. As we started to add more and more app servers to our stack, we started to hit this limit. So we wanted to write some software to better manage our connections to Mongo. We wrote a proxy for Mongo in Go. It's called Dwara. It has been tested with the Ruby and Go drivers in production. Go made it really easy for us to write this proxy because the I/O libraries are really good. It's very easy to write network programs in Go is what I felt. After that, we started rewriting our biggest beast, the API server in Go. Parse has around 50 endpoints. We started to migrate endpoints one by one. One engineer would typically work on one endpoint at any given point of time. Throughout the migration, we ran traffic through a shadow cluster. So the new upcoming Go binary would run in the shadow cluster. We'd send traffic both to our primary Ruby cluster and the Go shadow cluster, and we would compare results of what was happening. Once we had enough confidence on our Go cluster, we would promote it to be the primary. This shadow cluster was very useful for us. Through this, we found a lot of weird differences between our Ruby stack and Go stack. For example, Ruby supports weirdly formatted HTTP array parameters in GET. It's called rack style URL or something like that. Go obviously did not support it, so we had to implement it in Go because we had some customers depending on it. So we slowly started to rewrite, and our code base started to have funny looking comments like this because at times we didn't understand why Ruby did something. For example, this byte sequence is what Ruby expects. Yes, that's a pattern after the second 180 because Ruby, so on and so forth. Go was still a young language when we started using it. It had some really good libraries. I would like to point out the Mongo driver, MGO or Mango, and the Memcache driver were pretty neat. But we had some missing libraries. The Cassandra library we were using was not supported after a while, so we had to fork it and maintain it. I think Go did not have a very good story around stopping a HTTP server until 1.3, if I remember. So we had to build a bit of tooling and libraries around it. In the next section, I'll talk about a few of the libraries and tools we built. So as we started growing our code base, the problem we ran into most was we had to instantiate our object graph almost in every package and in every test package. This was really cumbersome for us to write. We had to also switch between mock implementations in test and real implementations in production. This was also kind of boring code to write. We had a few crashes in productions where we missed passing in a dependency to a struct, and this would crash when that code path was executed. It's kind of easy to do in Go because there's no explicit constructor. So we wanted to write something to solve all these problems for us. So we wrote a library called inject. Inject is our dependency injection library. It's a little opinionated. It works only kind of for singletons. We use it only at startup. We do not do any dependency injection once the program is up and running and serving requests. The philosophy is generally to fail at startup rather than to do any guesswork. So this is how our dependency injection example looks. As I said, anything which is a singleton or has only one instance of 8 running through the program lifecycle is a good candidate. In this case, it's a HTTP handler. Our HTTP handler depends on 2 things, a scribe client and a logger. Both of them are marked as injectable by using the struct tag inject. Once we run the main on this and inject the struct, actually, implementations for the logger and a concrete type for scribe client would be available to this program, and we can use it in the serve HTTP method. This is how our main for inject looks. We have an object called inject.graph. We provide it with concrete types or implementations of interfaces using the provide call, and then we call populate. What populate does is it traverses the graph and checks that we have implementations for all the interfaces. If it's not present, it fails. So all our binaries use this logic to boot. All our tests have a harness which use inject to boot, and that's how we write our code. The next problem we ran into was starting and stopping components in the order of dependency. We needed to start objects in a particular order. Again, doing this in every package, every binary by hand was cumbersome, was not bug-free. So we wrote a library to automate it. It's called start-stop. Start-stop relies on inject to calculate the hierarchy, and then it starts the object graph in that order. So if I show you an example, we have a scribe client which depends on something called a thrift pool. A thrift pool is basically a pool of TCP connections. We want that thrift pool is started before the scribe client is started. So when we use start-stop on this struct, what happens is start-stop figures out that thrift needs to be started first because it is a dependency of scribe client. It calls start if it is present on thrift pool, and then it calls start if it is present on scribe client. During stop, it does it in sort of a reverse order, where scribe client is stopped before stopping thrift pool. This has again helped us write tests quickly, write bug-free startup logic. Yeah. Another library we wrote is called Grace. Initially, we started with killing our Go servers when we wanted to do a deploy. Obviously, we lost a few user requests doing that. Our errors would spike up during deploys. So we wanted to do something better. Getting a load balancer involved would slow things down. So we built a library called Grace. What Grace does is, on a signal, it spawns a new process of the same binary, hands off the listening socket, and waits for the old binary to serve its request and die. We use Grace in all our Go binaries. It works very well for us. If you have the problem, go check it out. Another issue we ran into was errors from different parts of a stack in the Go could not be exactly related. We could not tell this memcache error came from this component. It was kind of hard for us to figure that out. So we built a library called stack error. Stack error basically gets the stack at the point of the error and wraps the error with it. We aggregate our stack traces in an in-house system called LogView to find out what's happening with our binary. This is how some stack error code would look like. We try to wrap all errors in our code base with the stack error.wrap call. So in this case, if we call the function error2, which basically calls the function error1, both of them return stack error wrapped errors. And when you print the error, it basically looks like this. It has both the stack traces from error1 and error2. Yeah, we use this to aggregate errors, find out what's happening, debug. Another common pattern we saw through our code base was batching operations and sending them asynchronously to some server. We wrote code a lot of times where we would collect objects in a channel, wait for some timeout, and send all the objects as one big request. Examples of where we saw this was in our metrics collection system, where we would, in the process memory, collect all the metric increments and send them as one batch request. Or in our billing logger, again, we would collect some n requests and send it out together. This was a common pattern, and we built a library to perform these operations in a batch. It's called muster. It has two tunables, basically. One is a batch size, the other is a batch timeout. When any of these are reached, a single request is fired for the entire batch. This library is pluggable in the sense the fire is a function parameter which you can basically give it and configure how the trigger function or the fire function works. This is the only place where we thought generics in Go would be useful for us. Because right now it deals with interfaces, and we have to cast it all over the place. But yeah. Yeah, so we built a few other libraries around HTTP control does a better job of, it's a better HTTP transport. It has timeouts and some connection pooling. Ensure is used to compare objects during test. Stack is used to collect stack traces. Yeah, we have a lot of other small libraries. You can go check them out at github.com/FacebookGo. So yeah, we love Go. This is Netik. He couldn't attend GopherCon, but he wrote a bunch of our libraries like Grace and Inject. So what are our observations or results of the rewrite? We converted a 130,000 line Ruby code base to a 175,000 line Go code base. It takes us around 3 minutes to run all the unit tests. It's down from 25 minutes in Ruby. All our unit tests are parallel. Our apps start in a few seconds instead of in minutes. We downsized our API server pool by 90%, and our rolling restart time dropped to 3 minutes. So how does parse look right now? We have around 500,000 apps built on parse. We see a 2 to 3x year-on-year traffic growth. We are primarily a Go stack. All our new feature development takes place in Go. Some more observations. Rewrites are usually hard. Your time estimates are usually off by 2 times. That's just heuristics. It took us 4 engineers and 2 years to complete this rewrite. But yeah, if it was a fun ride, we gained control of our code base. Now we understand what's happening. We built a bunch of libraries in Go. We all love Go, and we would probably write all our software in Go in the future. Go also has some nice side effects. Go compiles into a static binary. We can build it once and run it in all our Linux machines. So deploying with static binaries is easy. So we could go from a ops-centric deploy model to a developer-centric deploy model. where developers are responsible for deploys. So we deploy like multiple times a day now, and the time for changes to reach customers is fairly low. So this is a nice side effect. We kind of did not plan for it, but yeah. So to recap, we rewrote a bunch of our Ruby services in Go. We are generally happy with the performance. We reduced our API machines count by 90%. We have not been paged because of our API stack in a while. And yeah, that's it. This is one of our engineers burning a symbolic Ruby Unicorn server when we got rid of it, like I think last week, I don't know, yeah, sometime. So that happened. Yeah. So yeah, this is a blog post explaining all our libraries in a little more detail. So if you want to check anything out, just go to this URL. That's it. Thank you very much. Thanks for listening.